if Einstein's math didn't have an error in it like the one that you found, then the conclusion that he makes could potentially hold because the math holds and it's just a weird oddity of reality and here we are. But what you're saying is that the equations that he uses to make these conclusions are missing a certain internal consistency. And so the mathematical conclusion doesn't hold, therefore the second order philosophical conclusion cannot hold either because the math doesn't hold water. And so we have to rethink the entire basis for these relativistic strangenesses because the math isn't internally consistent.
Absolutely. And you're hitting the nail on the head on a very important point, which is if the math is consistent, which I argue it is not, but if it is consistent, Einstein was first. So he gets to define the interpretation. So if someone says Einstein's wrong and they don't challenge the math, but I want to challenge him because of I don't believe in the twin paradox or this or that, it's too late. That ship has sailed. He defined it, so he gets first right of defining what it means. We only get to change that if his math isn't right. And that's what I'm saying. And again, this is not to change someone's belief. This is to say, objectively sit with his work, take it to Wolfram Alpha, take it with a pen and paper, work the equations, and see if you get the same answers as I get. And if you do, then take the next step in that series of questions.
Do you think that you'd have an easier time if you pointed out that it was Minkowski who did the math and not Einstein?
You know what? There's a lot of debate in terms of who actually did Einstein's math. And I think it's there's some parts of it that are just absolutely brilliant. I'm critical of his work, but I think what he contributed in terms of how he approached things and just sparks of brilliance throughout. So nothing I say should take away from that. But he's human. And as a human, we could all make mistakes. And so this is just one of those cases where if we've made one, then let's correct it and position ourselves for wherever we go next in our scientific discovery journey. Right. So,
and then maybe reassess the interpretation. It's interesting you said that there has to be a fundamental fraction in the math for the interpretation to be shaken, because there are a few tantalizing examples where that wasn't the case. My favorite being heat, right? Because fluid dynamic equations describe the transfer of heat really, really well, but it's totally wrong, actually. It's not a fluid. And it was treated like a fluid, and they actually did a lot of work on these early thermodynamic engines using those equations. And they work. It allows you to make devices, and it's fantastic. But ultimately, some experimental evidence piled up to the contrary, where they weren't able to generate endless quantities of this fluid. They were able to generate endless quantities of this fluid by basically applying friction to the system.
It was a cannon bore.
It was cannon boring, I believe. And so every once in a while, it does turn out that the math is okay, but the interpretation itself has to be revisited. I think it's just much more difficult when you have some, demigod, some like huge monolithic mythical character like Einstein whose face is in every single 6th grade math classroom, or you're really, really fighting an uphill battle if you try to challenge anything about that.
That's right. And you're right about the interpretation as well.
And I assume that plays in, by the way, into how something can work but still be incorrect. That's like step 5 or step 4 or something. We'll get to that.
Yeah. Well, let's talk about that.
Cool.
So we've talked about what I thought was wrong, which was psi equals c times tau, an always relationship that when you actually test it isn't always. The root cause, because when he simplified his standalone tau equation and his psi equation with the embedded tau, he did that in 2 different ways. And number 3, why didn't we see it? Because we didn't recognize it as an average. And even if we did, we didn't recognize it in this format to really analyze what was going on. So those would be the first 3, objectively stated. And the 4th one, I'm going to give you an example. So when I was about 10, I'm dating myself here, this would be somewhere in the early 70s, my dad came home with a Casio calculator. And this was, home use calculators. And I know for folks nowadays it's like a calculator. I just have my cell phone or whatever. But at the time, it was a big deal to have a calculator in your house. And this calculator had 6 digits and it was all integer digits, unless you took this little toggle switch and you slid it to the side, and then it would give you 2 digits of accuracy. That was it. No more. 2 digits of accuracy. So it was great for balancing your checkbook or something like that. But if you're trying to land a lunar lander on Mars, it's probably not what you want to be using. So let's say that someone comes up with a theory. Someone walking along, they say, I have a theory. And it's before a theory is established. They say, I believe pi is 22 divided by 7. Okay, it's an interesting theory. Can you experimentally validate it? Sure, I have this calculator here, my parents' old Casio. Let's try it. 22 divided by 7. Answer, 3.14. Bingo, that's exactly what we should expect, 3.14. Perfect. So now we go around broadcasting, pi is 3.14, which is 22 divided by 7. In fact, I think I learned it as a crutch, very, very young age, that pi you could find by 3.1, divide 22 by 7. But it's not. And so someone now comes along and says, I don't believe that's right. I think I have a better theory. I think the theory is the circumference of a circle divided by its radius. And so let's try that. And you key it in the calculator and you come up with 3.14. Same answer. So you know what? 22 divided by 7 was here first. So it's the prevailing theory. I have no reason to be motivated to do anything else. The only way to know for sure is to understand, how did we come up with our expected result and our actual result? And what does the experimental device measure? Right? So our expected result, we said, was 3.14. Can we tune that better? So mathematically, you might write it as a series, and I'm going to do it as a simple series: 3 plus 0.1 plus 0.04 plus, et cetera, et cetera, et cetera, right? And I could do that for both theories. And depending on where I draw my horizontal line and truncate the rest of that, if I drew the line 3.14, draw the line, I can't differentiate my theories. But if I went 3.14 and went a few more digits and drew my line, maybe now I can differentiate my theories. Okay, so great. I have a way of differentiating my expected result. How about my actual result? Well, sorry to say, Mom and Dad, but the Casio calculator just isn't going to cut it. So I'm going to go out and buy my new HP Prime calculator and run it through that. And it gives me enough significant digits so that I can at least go up to where I've now cut off things. So that is interesting, because now when I run the experiment, I find that the person who was saying circumference radius thing is more accurate than the person who said 22 over 7. Okay, maybe I do need to change. So we can now say 22 over 7. Some people might go so far as to say it's wrong. I would say it's right to a point, and then it becomes wrong. So how does that apply to relativity? And for this, what we really want to look at, we won't go into all the math, but we look at his derivation of E equals mc squared. Very famous, very well tested, very well researched. But when you look at that, he builds a series. He basically says this plus this plus this plus this, and he has different terms where you have, c squared, c to the 4th, c to the 6th, c to the 8th, etc. He chops it off at basically c to the 2nd, which is where you get the mc squared from. So he doesn't show the c to the 4th term, c, etc. There's another set of equations that start with the exact same first term, but then in later terms, they differ. But he chopped them off, just like we chopped it off at 3.14. So at that chop off point, there's no way that you can differentiate Einstein's theory from another theory, different equation, but where it's been chopped off, it will now make the same prediction. So 3.14. The only way to have more accuracy is to look at Einstein's equation pre-truncation, look at the alternative equation pre-truncation, and have an experiment that looks at more significant digits to see which one is more accurate. So the argument is that it is accurate to a point, at which point it becomes inaccurate. And the research that I did on that was the Ives-Stilwell experiment, and it did confirm that the alternative equations outperformed Einstein's equations. So by performance, objective measure is going to be the difference between the actual result and the observed result. And so that error is how we would assess the objective quality, if you will, of the result.